Hello all. In this video of chapter coordination compounds, I'm going to talk about crystal field theory, factors affecting crystal field splitting parameter, colors of octahedral complexes, tetrahedral complexes, and application of coordination compounds. Crystal field theory or CFT. This theory is based on the following assumption. The assumption number one is the ligand will be treated as the point charge, and the interaction which is happening in between the ligand and the metal ion is purely electrostatic. There would be no orbital interaction between the metal and ligand. In an isolated gaseous metal ion, we all know that there are 5 d orbitals, which are dx, yz, zx, and other two are dx square minus y square and dz square. And all these orbitals are having the same energy level. That is why we used to call them degenerate orbitals. And when ligand approach to the metal ion, they used to create the crystal field around the metal ion. If it is the symmetrical, the degeneracy of d orbital remain intact, and if it is asymmetrical, the degeneration, or you can say the degeneracy, would be destroyed. The d orbitals will be split into two sets out of 3, and what all 3? dxy, yz, zx will be referred as T2g, and other two orbitals like dx square minus y square and dz square will be called as Eg. These two sets of orbitals, now they will be having the different energies, and the separation of energies of these two sets of d orbital is crystal field splitting parameter. It is denoted by delta O. O means octahedral. Now, the delta naught is usually depend upon the strength of ligand. Ligand would be classified on the basis of the strength as strong field ligand and weak field ligand. Strong field ligands are those in which the donor atoms are carbon, nitrogen and phosphorus. That means cyanide ion or Nz-1, carbon monoxide or carbonyl, ammonia, EDTA, ethylene dimethyl, ethylene diamine. These are the strong ligands. They cause the largest splitting of d orbitals, and pairing of electron is favored. These ligands used to form low spin complexes, whereas the weak field ligands, such examples like for weak field ligands are fluoride, chloride, bromide, iodide, thiocyanate, carboxylato. These are the ligands where delta O parameter is smaller to the energy required for the pairing of electrons, which is called as electron pairing energy. The ligands can be arranged in order of their increasing field strength, as iodide has the least, whereas the CO would be the most. Now, let's understand the splitting of d orbitals and the formation of octahedral complexes. Always remember, the octahedral environment of central atom ion is surrounded by 6 ligands, and the ligand approach the metal ion along with x, y and z axis. As the ligand approach the metal ion, the degeneration of d orbital is resolved. Now let's see. These are the orbitals. These are the 2 Eg orbitals, and these are 3 orbitals of T2g. Eg, the higher energy set of orbitals. T2g, the orbitals which are having the lower energy set. Delta O, the energy separation between the 2 orbitals, and the Eg orbitals are repelled by the amount of 0.6 delta O, whereas T2g will be repelled by 0.4 delta O. With a closer approach of ligand along with the x's, the doubly degenerated, that is Eg. What Eg? dx square minus y square and dx square. orbital experience the larger repulsion than the T2Gs. The delta O parameter is equal to dK units or splitting of T2G and EG levels, and these are the d orbital diagram for high spin and low spin complexes. This is for D7, for D6, for D5 and D4, and EG and T2G. The splitting will be occur in this manner. Now, what all are the factors affecting the crystal field splitting parameter? The magnitude of crystal field splitting depends on the strength of the liquid, whether it is strong or the weak. The stronger those appear in spectrochemical series approach closer to the central matter, which result in the larger crystal field splitting. Second factor is the oxidation state of the metal. The metal which is having the higher positive charge is able to draw ligand closer to it than the metal which is having the lower oxidation state. So the metal in higher oxidation state result larger separation of T2G and EG set of orbital. Trivalent metal ions cause larger crystal field splitting ion with the corresponding divalent. It is seen. Now let's talk about the color of octahedral complexes. The formation of octahedral complexes used to be accompanied by the splitting of d orbitals into T2G and EG. A separation of these two orbitals, delta O, can be measured from the experiment, and delta O correspond to the certain frequency of the electromagnetic radiation, usually in the visible region. A color of complementary to the absorbed frequency is this. Then it is observed. Let's take one example, and the example is hexaquo titanium ion or TiH2O6. The central metal ion titanium has electronic configuration 3D, and the electron occupies one of the T2G orbitals like this, and the absorption of wavelength of the corresponding delta O parameter promotes an electron from T2G level. Such energy gap in case of this complex is 20,300 centimeter inverse, and the complementary color of this imparted the complex, and the violet color would be arise due to the transition from D to D. Tetrahedral complex. A pattern of splitting of d orbitals, which is key in the crystal field theory, is dependent upon the ligand field environment. The tetrahedral structure having the metal atom M at the center and the 4 ligands occupy the corner. It is displayed like this. These are the 4 ligands, and now dx, xy, yz with their lobes lying in between the axes point toward the ligands, and other two ligands lying between the metal ligand bond axis. So xy, yz or zx, they used to have experience more repulsion, and the x square minus y square and z square will experience the lesser repulsion. And due to the large repulsion among xy, yz and zx, orbitals are having the higher energy, whereas x square minus y square and z square are having relatively low energy. Each electron entering in one of the dx, dy or zx orbital raise the energy by 4 dq, and that accompanying x square minus y square and z square orbitals lower down its energy by 6 dq compared to the hypothetical degenerate d orbitals in the ligand. The splitting of d orbitals in tetrahedral crystal field is much less compared to the octahedral environment. The crystal field splitting of d orbitals in the tetrahedral ligand is compared with the octahedral one. I said it is much less. Thus the pairing of electron is not favored in tetrahedral. For D4 electronic configuration, let's suppose the electron would occupy one of the T2g orbital. The low speed tetrahedral complex is thus not formed. Typical example like nickel tetracarbonyl nickel. It is the typical example where the shape is tetrahedral. The last topic would be the application of coordination compounds. In biology, several biological important natural compounds are metal complexes. For example, hemoglobin, where the central metal is iron, chlorophyll, where the central metal is magnesium. In medicine, platinum complex platinum is used in the treatment of cancer. Adita is used to treat the lead poisoning. We also use complexes for the estimation of hardness and water. Hardness of water is due to calcium and magnesium ion, and the ligand adita forms stable complexes with these two ions, and hardness used to be estimated. And the last is electroplating. Usually stable coordination complex on dissolution dissociate to small contact and furnish the control supply of metal ions. The metal ions, when reduced, clump together to form cluster or nanoparticles. And when the coordination compounds are used in the ligands in the complex, keep metal atoms always separated from each other. These metal atoms tend to form a protective layer on the surface. Certain cyanide complexes find, find application in the electroplating for these noble metals. Thank you.